I don't know either. Hello?
Nobody knows.
I don't know. Hello everybody, and welcome back to my channel of channels.
That was such a nerd moment. Oh my god, brilliant!
Guys,
I want to clip that.
It is 7:30 at night, and I have been studying since 10 o'clock this morning, non-stop. So if I am slightly incoherent, that is why. So that is why I have got NotJah on, and I'm not entirely sure if Ausman, are you still sound? Are you?
One
can people
incoherent person, one inebriated person, and then you've got Ausman.
Yeah. I know.
See, this show went to hell in a handbasket about
Pretty
10
much.
minutes ago.
Pretty much. All right. So for those of you who missed out on the stream earlier today, I have a 50% exam tomorrow for my advanced analytical chemistry subject. And so I thought, well, I may as well kill two birds with one stone,
praise Floof.
Praise Floof. So I wanted to do this and talk about the last two modules in my course. And the reason why I have NotJah on and Ausman is to keep it entertaining, because I don't think I can be entertaining at all at my current state of brain affairs. So I would say 100%.
Well, yeah,
we haven't started, mate. So anyway, so what I talked about earlier is chromatography. So chromatography basically is just a way to split up individual molecules in an analyte, which is something that you want to analyze. Of course, makes sense. So you split up the different molecules into bits, and you can figure out what those molecules are to when you split them up, basically. So basically, it's just separating individual compounds within an analyte. So mass spec is actually another way of being able to figure out what a compound is. It's generally destructive, and it is used to determine the molecular mass of a molecule, as well as the composition of a sample or the structure of a molecule based on the separation of charged ions in the gas phase and the detection of these molecules. Okay, so quick recap. A charged ion is either positively or negatively charged by it having an extra electron for negatively charged, or one less electron to be positively charged. So to find the ions in the mass to charge ratio, or MZ ratio. So they find ions. So if it's got a positive charge, mainly in mass spec, you're looking for a positively charged molecule, and it's really, really big. If it's like a really, really big and heavy molecule with that positive charge, its mass to charge ratio, or M to Z ratio, is really big. And if it's a smaller mass to charge ratio, it's smaller. So remember MZ ratio, and if anybody comes in on the stream, on the side chat, going, what the hell is she talking about with MZ ratio, just ping me and let me know, because I'm reading my notes here. And yeah. Okay, so what are some of the advantages of a mass spec? So it can study a wide variety of compounds directly and without modification. So with the chromatography, you might have to do something to the molecule to be able to separate it better, or the analytes might do something, make it more or less polar. But with mass spec, you can basically just look at these compounds without modification. And you can also perform the mass analysis and the structural characterization of mixtures without needing to separate them. So basically you can just chuck something in, like an analyte into a mass spec, and it can figure out the mixtures without needing to separate them, or you doing extra chemically stuff. It is quantitative, so it can figure out how much of a concentration a particular mixture is on happening. Oh, by the way, for those of you who are wondering what this beautiful steamy thing is, I read, and I believe this works, that if you have sound or a smell where you're studying and you breathe it in, or you smell when you go to bed that night and you sleep and you run it, it helps you consolidate the memory, and it makes quite a lot of sense. And the studies have shown that it improves recollection up to 20%. So if you are studying, that's a tip for you. Anyway, back to the. Sorry, what was that, Ausman?
The stream can. The stream can hear me. Okay, good. Jen is wondering if she could harass you too.
Okay. She wants to join in. Oh God, we'll never finish this event.
Miss, hey Miss, Miss. I got my hand up, Miss.
No, I know.
I wasn't listening. I wasn't listening, Miss. Can you say that again?
No.
Oh, but Miss, I don't want to fail, Miss.
You're not the one that's failing.
Yeah, but we're in class.
Yeah, now I can officially say this, NotJah. Nerd. Straight to
NotJah, yeah. Yeah, you can bring her in, but I don't think we'll ever finish this stream though.
Can you behave, Jen, if we bring you in? Let me know in chat.
Yeah, I don't think she will, to be honest with you.
Bum, bum, bum.
Bum, bum, bum. Okay. Okay. So it's quantitative, as I said, because it can figure out how much of a concentration of something is in the thing that you're analyzing, as well as qualitative, which is figuring out what you're analyzing. It's quite sensitive. I think it's.
Wait, what are we analyzing?
You went there.
Couldn't help it.
I know. At least you didn't say, what are we analyzing?
And now I don't even have to. I was going to, actually. I don't even have to say it in the chat. I can say it on your show. No, I skipped that opportunity.
Damn it. So it's a rapid anal analysis.
Now you're going to get caught up.
Damn it. So it's rapid. The timescales to record the data is between milliseconds and nanoseconds. So that's pretty.
Geez, that's quick.
That is very fast. So it can.
I was invited here for one reason and one reason alone. I will serve
and I
my
regret
purpose.
every moment of that. It can be combined with chromatography, and it's relatively easy to use, and it is common in labs. One of the downsides is the cost of the instrument is really high, and the sample is often destroyed, if not all the time. So, fun fact, the first mass spectrograph was the cathode ray tube. So cathode ray tubes, which I probably should have given to you to show the picture of this. So hey, Jen. Hey, Jen, you in? You can't hear us. Cathode ray tubes, they're basically sealed glass tubes from which most of the air has been evacuated, and then filled.
It's not my fault. It's not my fault Ausman brought up who he did. Okay? Yeah, no, I know. This is why I'm not naming them now, because we went live.
I said nothing.
You put it in my head. You put it in my head.
I did not think.
Oh, God, why did I do this? Oh, yeah. As long as we keep this, like, monetizable, they'll be fine.
Yeah.
Hey, Jenny.
You're very quiet, Jen.
Jen, you're really quiet.
I muted most. It's the microphone here. I'm staying muted as much as possible because there's people playing Borderlands 3 around me. So.
Fair enough. Okay, back to the story. So cathode ray tubes are sealed glass tubes from which most of the air has been evacuated, and then
They use them in
with,
old school televisions.
yeah. And they filled it with the gas of the element that we want to investigate. So a high voltage is applied to the tube, which caused the positively charged particles, the particles be positively charged, and they also generated a magnetic field. And this field actually bent the trajectory of the charged particle, and the extent of how far they bent it, the charged particle stream was bent, was dependent on the ratio of particle mass and its charge. So there you go, useless information for you. The first mass spec was the cathode ray tube.
Won't be the last of those.
Oh, what was that?
But please do. Oh, damn it.
All right. Okay. All right.
Everyone should know what a cathode ray tube is.
What was that, Jen?
I said.
I mean, yeah, like.
Cathode ray tube is that. Then I just realised there's lots of young people around who.
Yeah, I was gonna say maybe 30 years ago everyone would have, but maybe not nowadays. Technically we're old. We're all old enough to know the CRTs. So.
Yeah, CRTs. I should probably. I know a few people I could tell that entirely useless information to. Okay, so where was I? So the chemistry behind getting the molecular ion.
Can I ask a question, Mara?
Yeah.
Is smoking...
No, we can't start again. Sorry.
Is smoking the dope? It looks like there's smoke coming along from the side of you.
I swear to God, I'm not sitting next to him.
Are you stoned, Mero?
I wish. Okay, so just catching up on the chat. I am doing. Lizzie Lang says, "Mero, what degree are you doing?" I am doing a general science course majoring in stress, pain, sleep deprivation, crying, depression, as well as chemistry and microbiology.
On the side.
On the side, yeah. And so I'm not going to explain this for a while. I'm going to just torture Jen with why I'm smoking. Okay, so I'll talk about the chemistry behind getting the molecular
smoking.
Mero, we know that you're smoking, but why?
Her house isn't on fire.
So the chemistry behind getting the molecular ion. So what you do is they remove one electron, or give the molecular. They remove an electron or give the molecule. I say it's an electron here, but I've got a feeling it should be actually saying proton. So it turns into a molecular ion. So for those of you who are really confused what a molecular ion is, a molecular ion is a molecule that has a charge of positive or negative. Did I already say this? Because I swear I said this. I did say it? Okay. So what they do is they pummel the molecules with electrons. So I think I did actually give a picture. So Ausman, could you put up a picture? I think the first picture is the picture that...
First picture is up.
Is it? Okay, I'm just going to let it catch up on YouTube. So basically what they do with the mass spec is that they throw electrons at the molecule. And what happens is that the electrons get absorbed by the molecule, and then sometimes there's enough residual energy to break the molecule into fragments. So basically, it's kind of like a molecular scale version of what they did with the Large Hadron Collider. You know, how they they made things explode. It's kind of basically the same thing, but for a molecule rather than atoms. So these fragments are then read by the mass spectrometer. So, so the electrons that bombard the molecule are at really, really high energies of 70 electron volts, which I won't go into because that's another subject for another day. And it forces covalent bonds to break. Covalent bonds are the sharing of electrons between two nonmetals. So weaker covalent bonds, such as bonds that are polar, are more likely to break first. For those of you who don't remember or don't know what a polar molecule is basically on the periodic table, on the top right-hand side of the periodic table, which is here, you've got some really electronegative atoms. And so these atoms are just sucking those electrons towards them, like, just going, I'm really greedy and really, really hungry for electrons.
I know people like that.
What was that? Sorry, Jen?
I know people like that.
I'm like that with chocolate sometimes. Okay, that is the wrong picture, but that is totally fine.
I did that because you were mentioning the periodic table.
So when...
Hang on, what picture did you show? I hope it was appropriate.
it is perfectly. Okay, so as you can see on the periodic table, you have got the oxygen, fluorine, chlorine. They are all very, very electronegative because they just really want those electrons. And so when they're bonded to something, they kind of like pull those electrons towards themselves. And on the other molecules surrounding them, like the other elements surrounding them, are slightly positively charged, while the electronegative ones are slightly negatively charged. That is a permanent thing called a dipole moment, and because of their dipole moment, they're slightly weaker as well. So they're the ones that are more likely to break first. So mass spectrometry can only happen in the gas phase and with molecules that are lighter than 1,000 daltons. So, not mass spectroscopy. Bombarding the molecule with electrons can only happen with molecules that are lighter than 1,000 daltons. So a dalton is an atomic mass unit, which is 1/12 of a carbon-12 atom, which probably doesn't mean much to anyone, but basically a hydrogen is one atomic mass unit because it's got one proton and one atomic, so a proton and a neutron is one atomic mass unit. So if you lower the kinetic energy of electron bombardment to 20 electron volts, there'll be a lower yield of molecular ions formed and with less fragmentation, and this would not be reproducible, and there would be a higher MZ ratio. Okay, so another thing to do is chemical ionization. So rather than throwing electrons in a molecule, the source is filled with a gas of some description, usually methane or ammonia, which converts the gas into a variety of reactive products. Before I start doing that, does anybody have any questions? So Jonathan has
yeah, I have a question. I walked away for a couple of minutes. Do you want to repeat the last few minutes?
No.
Oh, damn it.
Come on, it was the best. No, it was the best bit. You got to repeat it.
Oh, how am I going to do my homework, miss?
With difficulty.
Fail now, you're going to fail.
All right, so I'm just waiting for the chat to catch up. Doc Fearsome says, hi, NotJah, how are you doing?
Hi, Doc. I'm doing all right.
And I'm saying hello to everybody on the side chat as well, and thank you for coming. Okay, So basically, there's a type of ionization called chemical ionization. So rather than throwing electrons at the molecule, the source is filled, donates a hydrogen using a reactive product. So the charge, well, basically what happens is they create CH5. So if anybody knows anything about organic chemistry, carbon hates having anything other than 4 bonds attached to itself. So 5 is pretty much breaking the laws of physics, more or less. So they do that by removing 1 electron from CH4, which creates a radical cation. So a radical, for everyone who's wondering what a free radical is a molecule with uneven numbers of electrons, and electrons prefer to be in pairs. So this cation of CH4 steals another hydrogen off another CH4 molecule, bringing the hydrogen and the hydrogen's electron with it, which creates that really, really unstable superacid CH5+. Because CH5 really, 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 really wants to get rid of that that hydrogen. It's actually what's called a superacid. So I don't know what its pH is, but it'd be in the negative numbers. So if anyone has watched my video on acids and bases, you'll probably I go deeper into acids and bases, but basically an acid is a molecule that wants to donate a hydrogen. So because CH5 really wants to get rid of this hydrogen, it kind of just goes, just fuck the hydrogen.
Yeah, it's so kinky. Now you've demonetized yourself. All your own fault, Mary.
It's all my own fault, yeah.
Yeah, if you pan now to the left, you will see a caterpillar sitting on a toadstool smoking your pipe.
Oh wow. So basically this molecule is just like just take it, and it doesn't matter how much another molecule doesn't want this hydrogen, it has to accept it because the CH5 and so the analyte is protonated, which gives it that positive charge, which is what the mass spec is looking for. This can cause the molecule to fragment, but it doesn't fragment as much as when they are throwing electrons at the molecule. So is there any questions? Jonathan Hazelton, yes, PK is very important. Hans P.S. Hansen, hello.
Hey,
everyone. Hans, I'm sorry.
No, I fucking up.
No, actually, this is the so everyone hates the poor hydrogens. Well, not necessarily. If you're a base, you'd love one. So if you're all about that base, no trouble. Sorry. Okay, so see this picture that's been down the bottom of the left-hand corner for goodness knows how long, and it's probably going, what the hell is it doing here? This is what's called electrospray ionization. So this is...
Say that again.
Well, do you want to say it?
No, because I
electrospray ionization.
Yeah, that one. Shut up, NotJah.
Yeah. Sorry, my
bad. Nerd. So electrospray ionization is a technique that allows larger and polar molecules. So remember when I was talking about the electronegativity?
I like polar bears.
No.
Sorry. I know it's because I wasn't listening before, miss. I'm sorry.
You would be the worst student. How do you even know how to read?
Well, because I'd steal the teacher's books and read them before they taught me.
No, that's true. All right. It's just like...
Mary, that sounds like electrosperm ionization.
Electrosperm ionization. Well,
you can't save this stream.
I really can't, can I?
I'm sorry, chat.
Trust Jen to be able to turn even friggin' chemistry into like something dirty.
But isn't that
Try
chemistry?
biology.
It's true.
A bit of both.
Never have
I must be high.
And a little bit of physics too.
I must be getting something from Marrow's smoke puffs because I just missed 2 perfectly good opportunities to fuck shit up.
I really hope people can hear what you're saying, Ausman.
Yeah, they just did. I made sure.
Okay, awesome. Okay, so electrospray ionization, or ESI for less Gen-ness. This is a technique that allows larger and polar molecules to be detected in a mass spec. So what's happening on down the bottom left-hand corner, you can see basically what happens is
I see something naked.
Is that you?
Well, no, look, on your picture, naked, charged. I can't even read the next. And it's too fuzzy on my screen, but
Okay.
something's naked. Thank you.
So basically
them
what's
naked particles. It's disgusting. They should cover up.
Dirty string. How could you show everybody that, Mero? That's definitely you're not getting monetized after that.
Yeah, definitely never going to be monetized. Okay.
They need to be wearing little bikinis.
God. So basically what's happened is that there's a stream. Don't you start. There's a stream.
Continue. We can continue.
The producer.
But you're gonna ring it.
The producer is ringing it in. Come on, guys. Come on, guys.
Ring.
Okay. So there's a spray.
Analytical?
It's an analytical spray, yes, and basically it's charged and it gets sucked into the machine, and what happens is that the solvent gets sort of like disappears. It gets
dissolved,
evaporated. So you've got so the solvent, you've got the ionized particles in the solvent and the particles get sucked into the chamber, and then it just breaks down and becomes more and more atomized and more spread out until the solvent goes away and all you've got are the ions.
Oh, so
sounds like a brutal battle.
I lost track of the conversation.
Well, you can always watch this later. Okay. So
For once I'm the one paying attention. What the
good stop there, NotJah. Okay.
Oh no. Fuck. That was a hiccup there somewhere. I don't know. It was a glitch in the system. I'm AI.
Okay.
It happens.
It's the Matrix. Blame the Matrix.
Exactly.
We will. Okay, so the analyte already has to be in the ionic form before it gets analyzed with the mass spectrometer. So there's no significant fragmentation in this. It's not really been damaged. The molecule has not been damaged, and it is suitable for the analysis of both small and large polar molecules. But the solvents and buffers need to be volatile, which means they need to be able to evaporate very easily.
So we need to buff our large and small polar bears.
Yes.
Got it.
All right. The next image will be the moldy, MALD. So moldy. I don't know how it's supposed to be pronounced.
Before we continue there, sorry, can I just ask about those polar bears? Do they have Coca-Colas?
No.
But, those poor polar bears.
I know. It's terrible.
They're missing out on everything.
Jonathan Hazelton says fragmented like this lesson. That's not my fault.
No, actually, that is your fault. You invited us and specifically asked for certain things. So you get what you ask for.
That is true. Okay.
That's
so
yours.
so easy with Mero.
Especially with my brain at the moment. Okay, so you've got. Oh, shut up,
I'm
guys.
not going to say anything.
So there's the MALDI is the matrix-assisted laser desorption ionization. Say that 15 times. So.
Oh, I thought we were talking about a whole different sort of moldy.
Yeah.
I was thinking of like a group of people. And I'm like, whoa, this changed very quickly, didn't it?
No,
yeah.
it's pronounced moldy, I think.
Yes.
It's pronounced moldy.
That'd be, yeah.
It's
that's
not
why that's what I
moldy.
legitimately thought that's what you were talking about for a second. I was like, oh wow, okay, this changed pace.
This changed, completely changed. No, it's the matrix assisted laser desorption ionization.
She proved it, everybody. The matrix is real.
The matrix is real.
It's real.
All right, the matrix is real.
So it's basically.
Oh wow, this has been an amazing stream, Barry. Thank you for that confirmation.
You've exposed it, and you've got 3 other Aussies here, and in front of all of us, you've just exposed the lie. Like, how could you? We've been working so hard at this. Yeah. Like,
I'm sorry. Thank you, Ausman. I appreciate it.
Go and get it.
Okay, so basically, it's what it does is it. Okay, I've lost my track of thought. It's basically a large biological molecule detector. So things such as proteins and DNA are embedded into a solid matrix. So like it's a sort of a solid matrix, basically. I can't really explain what it is. And then it gets shot by a UV laser. And that sort of, as you can see in the bottom left-hand corner, you've got the laser, the purple line hits it. It damages the surface of the matrix, and it releases the molecules that they're looking at, and then it carries it to the ionizer in the gas phase in ionized form. So it's ionized and it's in the gas phase. So some of the things that
hang on a sec, sorry to interrupt everyone. There seems to be an issue with the video.
Is there?
We've lost your video entirely.
Yeah.
Mine?
Yes.
We can still hear you, Mary.
Freezed.
We can still
I
hear
was
you.
going to say though, this version of the Matrix sounds so much better than the second 2 minutes.
You can still hear me? Oh, okay.
Just lost video.
I was going to say, I can look
it's not
up
terribly unattractive. Like, there could have been worse, I suppose. Anyway, hopefully that'll sort itself out. It says Zoom is not responding, but I'm not exiting this because last time I exited Zoom, it wouldn't let me come in. Okay.
Seems turn your camera off and on again.
Come back because
Mero.
I am sorry.
Mero, turn your camera off and on again in Zoom.
It's not even
responding.
It's not responding. I'm just going to keep going.
The whole Zoom is not responding.
Yeah,
the whole Zoom is not. Yep. Yeah. And last time this happened and I exited Zoom, I couldn't get back in. So I'm not going to touch that. If you can still hear me, that's good. Okay. So what was I talking about?
You were talking about the moldy.
The molding. Okay. So the matrix. So the matrix needs to be able to readily absorb the wavelength of the laser, which is not typically about 330 nanometers, and it also needs to have similar solubility characteristics to the analyte, and it needs to be able to donate the proton, which is how it becomes ionized to get into the mass spec. It should not react with the analyte, and typically, and it's typically a crystalline solid. So it's useful for biomolecules, so things like proteins, DNA, those sort of like things, but it's not really great with small molecules that aren't biomolecules of less than 500 daltons. It doesn't fragment the molecule, which allows it to be separated by of the mixed samples. So so basically what happens is after it gets stung by the laser, it goes gets introduced into the mass spectrometer, and it separates it into a vacuum according to the mass to charge ratio, or the M to Z ratio, which I mentioned earlier. So it's done by applying a strong magnetic and electric field in the analysis thing, and that accelerates and guides the ions towards the detector. The three main characteristics of an analyzer: it has an upper mass limit, it has transmission, and it also, I don't know why I wrote that. Ignore what I just said. Okay. Are you guys? Can you guys hear me? Can you guys hear me?
Yeah, we
Yes,
can.
certainly can.
Okay, cool.
Sorry.
We're just trying not to interrupt you.
Okay, fair enough. Okay, so basically what happens is, what's the one still? So can you go on to the next image? I think that's the time of flight. Is it the time of flight? Did I give you? Okay, all right. Well, I didn't send you a time of flight. So basically what the time of flight means is that the bigger the molecule, the slower it goes towards the detector. And that, yeah, so that's how they can sort of like do a sort of like a chromatography kind of thing, where the smaller the molecule, the faster it goes. Okay, so the next one is the quadrupole analyzer. But before I go on, is there any questions? So any questions for anyone? Nope.
And just so everyone knows, that is extended to the chat. If the chat has any questions, that is.
Yeah.
So it's not ambiguous.
Yes. So that's to everybody who has a question. All right. Yeah. So I'm just going to let the chat catch up.
Yeah. Chat, we are doing this also so you can have a little laugh and learn as well. So
yeah,
if you want to ask anything, please don't be afraid to at any four of us, and we will let Navadia know.
Yeah. Jonathan says he can't hear me.
Odd. That just might be.
That would not be a good thing. Can everyone else hear Navadia? Everyone knows you, Mero. Yeah, exactly.
Mero. Yeah, the thing is going. It says that it's picking up on you. I mean, not just when you speak, it picks up on you. When Navadia speaks, it picks up on her. Jen, can you speak?
Yeah, but if something about her Zoom has crashed and it's not going through to the live feed, that might be a problem.
No, but
if confirmation there.
If I can hear it, the stream can hear it.
Mm.
Fair.
Hello, Deuterus Stomach Catarini.
Are you streaming through like OBS or something there, or are you streaming direct through Zoom?
I'm doing it through OBS.
Yeah. Okay. The chat's caught up, and it says that I can hear everybody. Awesome. Okay. Okay. So you've got the quadrupole analyzer, which I'm expecting NotJah to start making dirty jokes about right about now.
Yep.
Yeah, insert dirty joke here.
So, okay. So, can you go on to the next picture for me, please? Because that's the time of flight.
Yeah, I've already got the next one coming up.
Okay. Sorry, there's a little bit of a lag on YouTube. So, okay. So basically the quadrupole analyzer is made up of 4 rods, which has like a hole in the middle. And the rods, they're connected through a radio frequency and a direct current potential. It uses the stability of the ion's motion in an oscillating electric fields and to separate and select ions for transmission according to their MZ ratio. So basically, hope you can probably see right then now is that there's non-resonance ion. It's not detected. It kind of gets caught in there, but the resonant ion goes straight through to the detector. So, all right, where are we? What are you're just giggling there. What are you giggling at? Yeah, fair enough. Yes, they are. Oh gosh, why am I not surprised about this one? Okay, so basically
ions as well, because you said you have resident ones. Do you also get squatter ones?
What was that? Sorry.
Yeah. Do you have squatter ions as well? Because you have resident ones, can you also get squatter ones?
Oh well, it's resonant, not resident.
One.
Yeah, no, we don't have any squatters here. There's a few that get lost, but anyway, what am I doing? I need to get rid of this. So I will continue talking. So basically, only ions of select M to Z ratios are able to reach the detector, and the upper mass limit is of the mass to charge ratio is about 3,000 Daltons. Then you've got, okay, NotJah, this is for you. You've got the quadruple ion trap. So that's for you. That's a setup for you, mate. Or not. Okay, Jen, that one's...
Sorry, I was messing around with my volumes. Is that better?
Yes.
Awesome.
So you've got the quadruple ion trap. So that's a variation of the quadruple analyzer, but it's bent back on itself to form a closed loop. And I think, have you swapped over to the next image there, Ausman? Yeah, awesome. So basically what happens here is the same thing happens as with the quadruple, only it goes straight back into, and it just kind of bounces around a bit, and
then it gets analyzed.
And then it gets analyzed, yes. So it gets trapped in the middle of the trap for a few microseconds, and then is sent in an unstable trajectory and exits the hole after being trapped in the analyzer.
Is that the whole reason why aliens like to do anal probes?
Possibly. They need to analyze us.
Right, I'm going to do a joke that NotJah missed out on.
Okay.
The quadruple ass analyzer.
That's it. That's true.
Well, obviously aliens if they've got quadruple asses.
Jonathan says, it's a trap. It is a trap. So it's actually more sensitive. So it's about 10 to 100-fold more sensitive than the other quadruple analyzer. So it's a trap that folds in on itself. And then you've got holes that are getting exited, and then it becomes more sensitive. Okay. All right.
I've got a whole heap of friends in the same room as me, and I've got headphones in, so they can't hear what's going on. They can only hear my responses. But I am very tempted to take the headphones out and put this on so they can hear and they can comment, because they are making comments on my comments, and some of them are bloody hilarious.
Okay. All right. So. Oh, okay. So, through my haze of just writing notes, I've actually gone back to talk about what time of flight, but I won't talk about it because I already have. Oh, okay. So actually, I'll go back to time of flight. So time of flight was that when Moldy was like hit the matrix, released the ions, and the smaller ones go faster than the larger ones, because they know how, like, they have a molecule of a certain weight and charge, they've got standards, and they're able to say this is how fast this molecule will go through and hit the detector. So they actually know, because it's consistent throughout all of physics, these particular molecules of a certain size will actually hit at a certain time, which I thought was pretty cool.
What are they hitting though? Because I missed that bit. I was too busy typing.
The detector picks up the time of flight.
In the mass spectrophotometry. Oh crap!
Yeah, the mass spec. Yeah, it's hard to say.
Mass spectroscopy.
That's the one. Yeah. Okay, so one of the problems with this one is that they don't always have the same kinetic energy, which means, of course, that they don't all move at the same speed. So what they do is that they can use two ways. They can either do a delayed, sort of like a delayed pulse, which kind of kicks the ones that are struggling behind up the arse and pushes them forward, so they can all hit at the same kinetic energy. Or the other option is to slow it down by using one of the coolest words I've read today, the reflectron.
I love that. That is an awesome
That's
word.
a reflectron. A reflectron.
Say hi to the chat. They wondered if you knew that you're in it.
Who was that? What?
Say hi, Steve. Hello. Yeah. Am I in the chat? Because they can see you behind me.
Steve doesn't want to say hi, Steve. This is strange. Julia.
You think we'd all be drinking, but we're not.
Oh gosh, I wish we were. Okay. So
hey, we should be. Why aren't we drinking, Stace? We should be. Hang on. We're going to change that.
I didn't bring a beer. I was about to say, if every time someone says something incorrectly, you take a drink. Okay, so the reflectron has a series of hollow rings held at an increasingly positive potential, which is terminated by grid. I couldn't find an image of this on the internets, so you're going to have to try and imagine what I'm trying to say. But basically, it's it kind of like is a reflector. It reflects off into the sensor, but there's like increasingly more positively charged grid, which slows down the faster molecules, and also so allows the slower ones to catch up. And then once they stop moving, they actually get flung into the sensor. So that is another reason why. That's another way to make sure that the faster molecules, like, they all hit at the same kinetic energy. Okay, so this is the Fourier transform ion cyclotron resonance mass spec. Ausman, can I get you? Oh crap, I don't know what is playing because I can't see because Zoom is not responding. Shit. Yes, this is the video. Yes, but I can't see what the video is playing because Zoom isn't responding, so none of you are moving for me either. So I will explain what it is, and hopefully I will be able to explain what it is at the same speed. Okay, so let me know when it... Booze is always good. Okay, so let me know when you start playing it, and I'll try to... Okay, so the sample gets introduced into the mass spec where it gets trapped in a circular, static, and uniform magnetic field. And so what they do is they kind of get trapped in this magnetic field, and then they start moving in a circular direction perpendicular to the direction of the applied field. So the smaller particles or particles with a smaller M to Z ratio will move faster in this field, which will then separate out further and further. When a radio frequency pulse sweep is applied to the transmitter electrodes, it will produce a cyclotron frequency signal. It is the most sensitive analyzer method in use today, with an accuracy better than 1 part per million. Using these calculations, the signal can be converted into a mass spectrum. Yeah, so that's how it works. So let me know when the video stops playing. It's still got a little bit long. So any questions with that one? Anyone? Any questions?
Sorry, I had a mouthful of booze.
Well, at least it was only booze.
Oh, shut up.
It's restarted.
That sounded wrong. But it probably was, so that's all right.
Okay, so is the video finished? Kind of. Awesome. Sweet. Thank you. So you got to remember, since the ions do actually have to move over large distances, everything is large to an ion, a high or ultra high vacuum environment needs to be maintained, which is expensive. So we've got to remember that. Okay, so we're going to move on to the detectors. So there are 2 types of detectors. One is a Faraday cup and the other one is an electron multiplier. So could you bring up the Faraday cup for me, please? Excellent. So basically a Faraday cup, it's a negatively charged cylinder.
What size cups does a Faraday have? A, B, C, D, double D, triple G.
Triple
F.
That's what I'd get, Nev.
Dear Lord, if there were really an F cup, I'd just be sitting there staring going, oh my God.
Oh gosh, I knew someone who had an H cup when she was pregnant.
Jesus.
Yeah, she was like, these things need to get, yeah, I don't want these anymore.
Yeah, so, that's back problems waiting to happen.
Yeah. So
no, please, nobody wish that you have big tits because yeah, it's not worth it.
No, it's definitely not worth it. Hello, Doorknob Head. How are you? And Badger, I hear is in there.
Badger.
Okay, so a Faraday cup is basically a negatively charged cylinder which collects positively charged particles when it hits it, and the current that is required to neutralize the negative ions is proportional to the number of cations arriving at the Faraday cup. Does that make sense to anyone? Did that make sense to everyone? Anyone?
I'm not going to get told off for that one. 2 girls, 1 Faraday cup.
Yeah. So did everyone understand that? NotJah? Ausman, are you guys there?
Not enough.
Okay. So yeah, it's
NotJah's always coming.
NotJah.
Oh, sorry, I had to run away for a second. Oh no.
That's all right.
That was so he could come.
Oh, I forgot to write it in the chat. My bad.
That's all right. So yeah, the cup is not very sensitive. So the more common and more sensitive one is the electron multiplier, which is the next image. So what that is the cations, which are the positively charged ions, they strike a dynode. So that's the electrode in a vacuum tube, which liberates the electrons, because everyone needs to be liberated. Electrons need to be liberated, which then causes more electrons to be produced, which then produces more electrons, which then produces more electrons. And so a series of these dynodes multiplies the electrons by approximately 10 to the 5 before they reach the anode. And this is
Like
much more
10,000 times.
10 with 1 with 5 zeros after it. So yeah, 10,000.
Yeah.
Yeah. So
No, that's 100,000. Sorry.
Yeah.
I should know.
Yeah. You're right.
I'm a maths geek. Sorry.
I Jen.
promise I have only had one, and I haven't finished it.
I am ashamed at you, my fellow nerd.
Yes. My excuse is that I've been doing studies since like 10 o'clock this morning, and it is now 8:30. So that's like 10 hours worth of study. So yeah. So anyway, so it's the 10. So going on to the next one, you've got tandem mass spectroscopy, and so basically it's what it is. So it's a coupling of multiple mass analyzers. So
there are a couple. Oh, that's adorable.
I know.
Oh, so sweet.
No, coupling.
Coupling.
No coupling. You get little
So
we'll let it go.
So basically, it is what it says. It's like the most commonly used one is to isolate a precursor ion of the desired MZ ratio. So some people in the chat, I'm just going to go over what the MZ ratio is. The M is the mass of the molecule, and Z is the charge of the molecule. So it's generally a +1. So the mass could be 240 AMUs or atomic mass units or Daltons, and then the ratio of 1. So that's what the MZ ratio is.
It also sounds like a rap. From the M to the Z.
That is true. Okay.
I'm not going to remember any of this. I am so sorry, Mary.
That is fine.
Not really. At least you can blame me if you fail.
I will, actually. I will. And me not actually arriving to any of my lectures for like an entire 6 weeks has got nothing to do with that. Hey.
You're going to blame me as well, okay?
I will definitely blame you for that. Okay, Critical was screaming at me because okay, Orla says Critical was screaming for you because I asked when I can get laid because Navadia asked if there were any questions. Oh, okay, so that was in the chat. That was from Orla to Bad Tempered Badger. Okay. All right, so the most commonly used is to isolate a precursor ion with the desired mass to charge ratio. Then that undergoes fragmentation to generate product ions, which is then analyzed by another mass spectrophotometry. There's definition again, MS. So this is used.
Sclerosis?
Mass S.
Oh,
it is a hard word to say. It is a hard word to say. Okay, so this is used for structural, trying to figure out what the structure is of unknown molecules, and also with working with sample mixtures as well. So basically what's going on is they can be spatially separated in instruments. So the instruments are just separated that have been connected by vacuum tubes. So the analyzers can be quadrupole or time of flight analyzers. They especially the quadrupoles can act both as analyzers and collision cells as well. So collision cells are the chambers in which the ion path between the MZ separation elements in tandem with the mass spec in space configurations. If someone can actually tell me what that means, it would be lovely.
You'll have to repeat it.
So all right, I'll repeat what I just said. Collision cells are chambers in the ion path between the MZ separation elements in tandem with mass spec in space configurations. So if an ion collides with a neutral atom, okay, here we go. If an ion collides with a neutral atom or molecule, such as helium or a noble gas, part of that ion's kinetic energy can cause the covalent bonds within the ion to break. And these are often used in mass specs for biomolecules such as DNA or oligosaccharides.
Yeah, so you fire the ions into the mass that you're trying to figure out what it is, and then you can see the results of the ions that separate.
Yeah, and it collides with helium and argon, and because they're a neutral gas, they don't get
react, but they absorb the extra.
Yeah,
and they give off light, and then you can measure the light to see what's.
No, this is mass spec.
Yeah, but mass specs still use light emissions to figure out what things are, don't they? Light emissions that come as you should know this.
I'm just letting you continue until I point out the fact that the reason why that the detectors are get neutralized.
Yeah.
Remember the Faraday cup?
Yeah, but don't the detectors work by detecting the photons that come out when the electrons change their valence shells?
No, you're probably thinking of UV Fizz spec.
Okay. I just thought because it's spectroscopy, I know it's mass spectroscopy. I thought
this is mass. Yeah.
Yes, I realised that, but I thought they still use the same technique, but they energize the ions in such a way that they respond in a way that you can measure the masses and stuff like that. So isn't the detection in the way that the gas changes done by the ions that the photons they emit, and then they measure the photons, so they actually look at the spectrum that comes out of the test results based on the way it energizes.
No, so
I've misunderstood. You have to correct me.
So what it does is So remember how I was saying about the Faraday cup? It picks up the cations hitting it, and then the cations, because they are positively charged, the Faraday cup is negatively charged, and when the Faraday cup gets hit by the positively charged ions, the charge changes, and that's how and by going by the charge that changes, that kind of tells you how many ions that has hit the
so they detect the change in the charge of the cup to determine the mass. Why don't I say spectroscopy as part of it then? Because spectroscopy would, I'm going to look this up later. Why
look it up now, because you could be right, but that's what they've given me in my lecture notes.
All right, I'll look it up whilst you keep going.
Yes, and then let me know. Okay, where am I? So okay, can you go on to the chromo? Can you go, Ausman, would you be able to go to the chromatographic mass spec, the three-dimensional image and transitioned? Excellent, we like that.
Okay, it depends on the type of spectroscopy, and the original type was used photo ions, which meant they could detect the changes in valences, which is what I was talking about. But there are other types, and they're all called spectroscopy, so it's a hangover.
Oh, okay, fair enough.
So I'm ignorant that I wasn't completely ignorant. Thank God.
No, fair enough.
No, I can't say thank God. There isn't one. Any monster? I don't know.
Anyway, so you've got the okay. So this is a mass spec of a analyte that has been separated by chromatography mass spec. So for those of you who are not sure what I mean by that, is chromatography is the separation of molecules in an analyte. So every, like, an analyte might have like a whole heap of different...
just what you said, anorak.
Hi, Terry.
So you separate them in an anorak. Because they're flashes.
So basically, so the chromatogram shows the different peaks and the different mass specs. So that's how you can get the the chromatography thing going on there. So basically, it's coupled. The chromatographic mass spec is coupled with both gas chrome and HPLC, which is a conversation I had earlier today, and I'm not going to go over that one. And it usually undergoes.
I haven't watched it yet. I'm joking. No, please don't.
I'm just no. just understand that chromatography sort of splits up the molecules that are within an analyte.
What's an analyte? Because
the thing that you want to analyze.
Oh, okay. That's fine. That makes total sense. Thank you.
Okay.
Analyte. It's an.
Hey, I actually asked a serious question. There's something wrong with me.
Oh my god.
I'm serious. No, it doesn't happen.
Hey Jen, an analyte is an anal light.
Dude.
That you did, Ozzy. yeah. It may not be the sun, but you can sure read by it.
I had to get it. I had to get the naughtiness in there somewhere.
Oh, you guys are terrible. Anyway, let's continue on.
Because he believes that the sun shines out of his ass.
Okay, we're almost finished. I've got like a page to go.
No. I'll try not to interrupt.
Okay, so
interrupt, just like that.
So the chromatographic mass spec usually undergoes hard ionization through electron impact. So it splits up the molecules and breaks them up rather than keeping the actual molecule that is, different size. And
I love doing that head's comment. Anal light, anal for beginners.
Dawn of Head, gosh, you crack me up.
Now, why didn't I think of that?
Just the tip.
Just the tip.
She can keep the tip.
Okay, so the mass spectrum is a graph that shows the relative abundance of ions versus mass to ratio value. So mass to charge value ratio values. So if you can see in this picture, you've got big spikes, and the higher the spike, the higher the mass to charge ratio. So so that's basically what it shows. So I've got a bit of terminology and then a little bits of here and there, and then we're going to go because my brain has decided to melt out of my ear. Okay, so you've got the molecular ion is an ion formed by the loss of an electron from an entire molecule. You've got the base peak, which is, if you look on the mass spectra, is the tallest peak of those individual mass spectra. So the for example, the blue one, it's sort of like towards the left-hand side.
Did you just say you blue one?
No, the blue one.
Oh, the blue one. Okay, sorry.
Bad Tempered Badger says, or is it someone tentatively agreeing to anal? Anal 8.
All right.
8. Can't do it. I'm not English. I can't say that.
Anal 8.
8.
Sounds like a song.
Okay.
Sounds like a song. Anal light.
Oh gosh. Oh. Okay, so that's the base peak. That's the base peak. I'm going to continue on. Okay, so you've got your radical cation. So it's radical. It's crazy. It's your positively charged molecule with an odd number of electrons.
Are you positive about that?
I am positive about that because cations are always positively charged.
Okay.
And so
that figures for cats. I would have thought snake ions would have been positively charged too.
Yeah, that's true. Well, anions, the way I remember anions and cations is sounds a bit like onions, and when you cut onions, you start to cry, and that's a sad thing. It's bad. And
cats make you feel good, so that's positive.
And it depends on who you are. Sometimes a dead cat makes you happy too. So,
and Schrodinger's cat can be in multiple places at once, and occasionally dead.
Yeah, and alive at the same time.
And alive at the same time, yeah.
Okay, then you've got your fragment ions. So these are cations formed by the decomposition of the molecular ion. They often correspond into stable carbocations. So a carbocation is carbon that is positively charged. So it doesn't necessarily mean it is a single carbon that is positively charged. It could be like a group of carbons where there is one that is positively charged. So you've got different types of masses. You've got your nominal mass. So the mass of a molecule is the mass of the molecule is the integer masses. So I'll see if I can explain this because I copied this straight from my notes. Okay, so every molecule, all right, a molecule is a thing that is made up of different elements. Every element or every atom has its mass. So if we can go on to the periodic table, that would be awesome. Ausman?
Is a periodic table a chart that you use to keep track of your cycle?
I have no idea.
Switched.
You switched? Awesome. Okay. So so the mass of a molecule, for example, you've got water has a atomic mass of 18. So oxygen is 16 atomic mass units, and hydrogen is 2 is 1 atomic mass units. So, and there's 2 of them, so that's why it's 18. So the nominal mass is the molecule that has the integer mass with the most abundant isotope. So an isotope, for everyone who doesn't know what an isotope is a element that has an atom that has a different number of neutrons. So a neutron has 1 AMU, and a proton has 1 AMU. So this is, I hope I'm making sense.
Yeah, you mean an atom with 2 atoms which have the same number of protons but different number of neutrons.
Yes, exactly.
Neutrons.
Neutrons. Yes.
Yes.
They're different isotopes.
Isotope, which is one that it normally is, and you can have variance in the number of neutrons, which is what gives you different isotopes.
Yeah. So we identify.
I was less clear than you were. Yeah.
You definitely were. So
that's my corner now.
No, I appreciate that, Jen. Thank you. So for example, you've got carbon 12 is the most abundant isotope of carbon. So it's got 6 neutrons and 6 protons. However, so the nominal mass of carbon is carbon 12, but since there's lots of different types of carbon, so you've got carbon 13 and 14, which are different isotopes.
14 is the one we use to age organic matter.
Yes.
14 is the
13. No, isn't it 13?
Carbon dating is the only type of carbon dating that Kenham believes is real. Despite the fact it's exactly the same technique, just different atoms.
Yeah. Let's not talk about that person. So if you can look at carbon, so carbon is on the top right hand corner next to boron and nitrogen, in between those 2. I know this is so boron, but tish. Anyway,
Mary told a dead joke.
So boo. So you've got, so you can see there how carbon comes up as 12.011. That's taking into account the other isotopes of carbon. The nominal mass is basically the round down or to just an integer, which means so it's just 12, or nitrogen will be just 14 and oxygen will be just 16. That's sort of like a rounding off to the closest whole number. Okay, so then you've got your monoisotopic mass. So that's the sum of the exact masses of the most abundant isotopes of the constituent atoms. So for example, what I was saying earlier, the masses of the most abundant isotopes of hydrogen is 1.007825. Carbon is 12 exactly, and bromine is 78.918366. So that's the masses of the most abundant isotopes of a particular element. So
what's the atomic mass of a bromine?
A bromine?
A bromine. Ozzy knows what a bromine is.
Bad-tempered badger. Are you completely confused, badger?
No.
Absolutely.
Awesome. That's good. That I aim to please.
I've got a little side note to add when you're done.
Okay. So basically what they're saying is the monoisotopic mass is the sum of the exact masses of the most abundant isotope, but not the lightest, because sometimes you can the most abundant could be heavier than the least abundant or a different abundancy. And then you've got your average mass, which is basically your atomic mass units that you will see on the periodic table. They don't change a lot, but they are actually important with mass spectrometry because we are looking at weighing things to the 1 AMU or the 1 Dalton. So you need to remember, like, we need to understand that even though we might have a mass spec, if there is a different isotope, it'll come up in the mass spec because it's really, really, really sensitive. Okay, so that's pretty much everything that I can say without going into extremely complicated protein science. So I will actually leave it here. So thank you very much, everyone.
Also, I'm just going to add an interesting aside to what you're talking about with atomic masses is most people, now after all the stuff at CERN and everything and finding the Higgs boson, that most people tend to think that the mass of atoms comes from interaction of molecules of atomic nuclei with the Higgs field, but that's not actually true. Most of the mass of a particle actually comes from the energy contained within it, because as we know from E equals mc squared, mass and energy are equivalent. So energy within the atom that creates most of its mass. The problem is there is a difference between the energy we can know that there is in an atom and how much actual mass there is. And that was why the concept of the Higgs boson was developed, because we needed a mechanism to allow for this extra energy. So most of the mass of an atom is the energy within the atom, and a little tiny bit of the mass is interaction of that mass of that atom with the Higgs field.
Interesting.
Interesting bit of physics there to add to your chemistry.
Thank you.
Sorry.
All right.
Curious again for a second.
No, I appreciate it. I like these little bits of useless information.
Yeah, I have my heads full of them.
So I just want to say thank you for everyone for coming and joining in on this stream. I really appreciate it. And to everyone who has decided to drop in, do their talking and stuff on the side chat. Thank you for listening to me rambling about science. As I said, this is a 50
fun and completely nerdy, and I love it.
Yeah, I do have a 50% exam tomorrow, and I needed this. And I like talking about science because science is awesome. So Jen, can you shill yourself for me, please?
Okay, I'm Jenny from Jen's Little Corner. Go follow me on Twitter at Jen's Little Corner, or you can find me at Jen's Little Corner on YouTube if you want to look at my YouTube channel. One thing I will share is I am aiming to do an interview with my mum whilst I'm visiting family, and I wanted people to post a few questions on the thread that I've got in Twitter to ask my mum. Please be nice. My mum is a theist, and
she's
also
really
my
lovely.
mum, so be nicer because she's a lovely person.
And she's also supporting something that's going on in the background with between Jen and I. So she's helping us out with something with that.
Yep.
And yeah, so she's really lovely. Even though I have not spoken to her, she's actually,
I can do sometime there.
Yeah. Yeah. So support.
So if you want to catch up on the thing, check out my Twitter. Throw me a few questions. If there's any that's a bit rough, I will not ask them. But,
is it a pinned tweet or?
I will pin it. Yes,
Okay,
I will
awesome.
pin it, and then you guys can find it and throw me a couple of questions to throw at. I think the only person who's actually asked the question so far is Jay, and yes, I wouldn't mind a couple more to throw.
Okay, awesome. Sounds good.
Thanks.
Awesome. And Ausman, would you be able to shill yourself?
Absolutely. I am Jan from Ausman Cometh. I don't know why I just fucked it up. Anyway,
did you just say I am Jan?
Yes, I am.
Not
Jan.
Happy Jan.
Yeah, from not Happy Jan. That is half the reason why I chose my new name of Jan.
Just want to point out, I am Cometh, man. It sounded a lot like Mein Kampf.
It was nearly that. It was a mixture of Mein Kampf.
That if you wanted to make sure that Mara got demonetized.
I didn't mean to say it like that, but it came out like that.
And thank you, NotJah, for actually saying that. So,
yeah,
right at the end of the stream, good one, dude.
Okay, man.
Yeah, I am Jan from Ausman Cometh. I've actually said that name right for once. I am doing a fundraiser soon to replace my computer. This time, I was able to fix the issues from last stream. But they will come back. Please give my video a look. You don't have to give me any money. Even just liking the video is okay enough. Also, make sure to give all of these lady lovelies and this crazy bastard next to me, NotJah, a good subscribe and a good follow. Because that'd be really good.
Okay. And NotJah, can you shill yourself?
Well, I'm NotJah Witness. I do NotJah Witnessy things sometimes. Do all the ats and the follows and the hashtags with NotJah Witness.
Okay, cool. Links are in the description except for Jen's. I'll update that when we finish the stream. So my name's Meredith from Nevada. Thank you very much, everyone, for coming, and have a lovely day, evening, night, whatever. And don't forget scandium, iodine, nitrogen, and cerium. Tick. Bye.
Bye.
Bye.